Okay, this is section 3.1. This is our first section in chapter 3. It's really a continuation of our applications of derivatives. This is going to be an introduction to maximum and minimum values, specifically using calculus. Now we're going to go ahead and define maximum and minimum values, and some of this is just going to seem, well, at least it should seem relatively obvious, things that you kind of have an idea of already, but we are going to define them mathematically. And we're going to put some math terms to it, but it doesn't necessarily mean that you have to memorize the math terms. You just have to understand where they're coming from. So I'll do my best to explain them as we go. All right, so we are going to define and apply derivatives to find extreme values of functions, and we'll get to that. The first thing is, let's just talk about maximum and minimum values in general. So optimization, meaning to optimize something, problems are an important application of calculus. So we're going to be required to find the best way of doing something, finding the optimal way of doing something, optimizing. Some examples might be, what is the shape of a can, like a soup can or something like that, that can minimize manufacturing costs? You can see how that might be something a company would be interested in. I want to minimize the cost of manufacturing, because then obviously you're going to be able to get more revenue, more profit if you minimize your cost. Or you might want to figure out what is the maximum acceleration of a space shuttle. I am sure that the astronauts who go up in the space shuttle are glad that there are people who know this information, because otherwise they could technically rip the shuttle apart if they try to accelerate too fast. So again, very important information, and all this can be done using calculus equations. So these problems can be reduced to finding the maximum or minimum values of a function. Maximum or minimum values of a function. All right, so here we go with our mathematical definition. And again, I'm going to give you the definition, and then we're going to go back and actually try and make sure it makes sense. So a function has what is called an absolute maximum, also potentially called a global maximum. Sometimes you might just hear it called the maximum. I'll explain why it could be called the maximum as opposed to something else. So a function is going to have this thing called an absolute maximum at C if f of C is greater than or equal to f of x for x in D, where D is the domain of f. Okay, so we're going to stop right there and think about that for a second. F of C is a y value evaluated at C. This is saying that the y value at our x value of C has to be greater than or equal to all other y values, f of x, is on the function. That should make sense. If your y value that's given to you is greater than or equal to every other possible y value on the function, it will be the absolute maximum value of the function. It's going to be the highest possible point on the function. The number f of C is called the maximum value of D. Okay, so this is important because when they ask for a maximum value, right here, when they ask for a maximum value, you are looking for f of C, which is a y value. So when they ask for a maximum value, they're asking for a value, a y value of the function, not the x value. The x value, or the C value, which is the x value, is where it's located. It is not the actual maximum value of the function. So you want to give a y value when they ask for the maximum value of the function. Similarly, f of x is going to have, sorry, I lost my place. Similarly, f of x has an absolute minimum at C if, just like before, f of C, or our given value, is less than or equal to all other f of x points for x in D, and the number f of c is called the minimum value of f on D. So again, just look at your inequality. In the minimum, f of c, the one that you're looking for, is less than or equal to all other possible f of x values, which means it would be the absolute minimum. So the maximum and minimum values of f are what are known as extrema. Root word being extreme. Hopefully that makes sense. The extrema being the absolute maximum and minimum. Okay, there are some of your mathematical definitions. Now let's take a look at it graphically. As far as something like this, I really do think this is going to make sense to you, but there's a couple of other things that we're going to talk about that we haven't really introduced yet. All right, looking at this first graph, the curved one on the top, we can figure out where, just by looking at it, the absolute highest and absolute lowest points on this graph are. You should be able to just see this. Okay, there is an absolute maximum right up there, and there's an absolute minimum, the lowest possible point right there. Now, in this case, the ends do not keep on going. Those are stopped. So that's the lowest point on the left, and the highest point is the one I circled up on the top. I'm going to get rid of those here for a second, because what we're going to do is we're going to label every single one of these things. So right here at the end, we're going to call that A. Okay, right there in the middle where this thing goes to a little peak, we're going to call that B. We're going to call the point C right here, what would be right there kind of looking like it's on the y-axis. We're going to call this D, where it looks like it goes up to another peak. We're going to call that one E, where it comes down, and then we're going to call the end point here F. So it looks like our endpoints are A and F, and then we've got these peaks at B, C, D, and E. So we want to establish what the absolute maximum is. The absolute maximum. The absolute maximum, if I'm asking you what the absolute maximum is, it is going to be a y value. Well, we know that it occurs at D. We've already kind of shown that. But what is that value? Well, it's going to be whatever the function is evaluated at D. So the absolute maximum will be f of D. Likewise, the absolute minimum. The absolute minimum will be at the lowest point. Well, we know that it occurs at A, so the actual absolute minimum will be f of A, whatever the function is evaluated at A. Okay, and that's pretty much it for absolute maximum, absolute minimum. Not too difficult to see. Okay, we're going to go down to the second graph. We're actually going to come back up to this graph here in a second to do something else. We're going to go down to this graph. This one will be a little bit shorter because there aren't that many places we're going to label. We're going to label the left endpoint as A. We're going to label that first corner peak there as B. The second one will be C, and then the other endpoint we'll label D. Okay, and if you haven't already done so, to kind of help yourself along, go ahead and list the absolute maximum and the absolute minimum. Okay, again, I'm hoping that you can see that pretty quickly. The absolute maximum is the highest point. It occurs at D, so the maximum would be f of D. The absolute minimum is the lowest possible point, which occurs at C, so it will be f of C. Okay, not really that difficult to see, at least I don't think so. I hope that you guys agree with that. Okay, we are going to use these graphs again in just a minute. We are going to define something else now. So it says, a function f has a local maximum, or what is called a relative maximum, at C if f of C is greater than or equal to f of x when x is near C. This means that f of C is greater than or equal to f of x for all x in some, this should not be there. Let's get rid of this. In some open interval containing C. Similarly, f is going to have a local minimum at C if f of x is less than or equal to f of x. So I keep saying f of x. If f of c is less than or equal to f of x when x is near c. Now you might look at this definition and say, wait a minute, this is exactly what we just did. Well, it's close. It's very close. For the first one, when we're talking about a maximum, first of all, it is a slightly different definition called a relative or a local. Relative or a local maximum. And look at the difference in the definition. Yes, f of c still has to be bigger than or equal to all other f of x's, but this is the important part right here. When x is near c, so it is not necessarily the entire graph. It's just in a localized region around whatever the c value is or whatever our x value is. So we're actually looking for a local or a relative maximum, or in the case of the second sentence, a relative minimum, again, when x is near c. All right, so let's go back up and look at that. Now, I want to make sure that you guys understand that does not necessarily mean the c that I put on the graph. That just happened to be another letter. C represents any one of those x values along the graph. So now let's take a look at this. We already know where the absolute max and the absolute min are, but we have relatives as well, relative max and relative mins. So it looks like right here, right in that little localized region, if you just focus in what I kind of put in that parentheses there and ignore the rest of the graph, you can see how it looks like it's got basically just a little peak in between those blue almost parentheses or whatever you want to call them. So that means that at B, you're going to have a relative maximum because it peaks going up then back down again. It peaks there. So we're going to have a relative maximum at B. So the relative maximum value itself would be f of B. But that's not the only place on the graph here that I have a relative maximum. I also have a relative maximum right there at D. And it's okay that it's also our absolute maximum. I'll explain that in a second as well. Looks like we have a relative maximum not only at f of b, but f of d is also a relative maximum, because you can see how if you just focused in on that second set of parentheses there, within that region, I've got a maximum. Now, I want to make sure that you see this. We do not have a relative maximum at f. And the reason for that is this. I cannot create an open interval, which is why I've been using parentheses, around f. Okay, I cannot create an open interval there because, as you can see, to the right of f, there is nothing in the graph. So an endpoint of a graph cannot be a relative max or min. I will say that again because I'm not writing it down here. A relative max or a relative min will not occur at an endpoint. It can't, because you have to be able to surround it. And at an endpoint, one of the sides will be completely open. Okay, you can have an absolute at an endpoint, but you cannot have a relative because it must be able to be surrounded by this open interval. Okay, so we've got, let me erase that because that's not really a relative. We've also got relative minimums. Okay, I have a relative minimum here because I can surround the values there at C. I can surround those with an open interval, so it looks like I'm going to have a relative minimum at C, so it's going to be f of C. It's the lowest possible point within that localized region in the parentheses there in that open interval. I also look like I have one here at E. Okay, and there are no other relatives on there. Again, A cannot be a relative because I cannot surround A on both sides. I could put an open interval on the right side, but I can't put one on the left. So A is not an relative. It is an absolute. Okay, let's go ahead and do that with the graph below. Again, should not be that difficult. Let's list our relative maximum values. And it looks like I've got one right there. Now notice this occurs at a corner. It's okay. It doesn't, just because it's not differentiable there does not mean it's not a maximum. It's still within that region. It's the highest possible point within that localized region. So it looks like f of b will be a relative max. And I do not see that we have another one. Okay, and also at C, it looks like I can create a relative minimum. So f of c will be our relative minimum value. And again, in this case, the relative minimum and the absolute minimum were the same. So one of the things that I like to kind of give a real life example of, most people, and if you don't know this, then you're going to learn this for the first time, most people know that within the state of New York, the city with the largest population, or the maximum population of any of the cities in New York, happens to be in New York City. Okay, most people do know that. However, most people also know that within the country, the United States, the most populous city in the entire country is also New York City. So it just happens to be a relative maximum for New York State, but it's also a global maximum for the United States, or an absolute maximum population for the United States. So they can be both. That's just kind of one really quick, I think relatively easy example to let you understand how one can be the other. It doesn't necessarily mean they will be, but they can be. Okay, I think we're going to do this next example, and this might be the last example before we go to video 2. So looking at example 1, graph the function on the indicated interval and identify the local maximums, local minimums, as well as the absolute maximums and absolute minimums. Now, I am not going to make you graph this by hand right now, but it would be a good idea if you could learn how to do so. But we haven't gone over enough stuff yet to actually make you graph it by hand. So you can go ahead and plug this in your calculator. However, once you do that, I just want you to use that as the sketch for your graph. So if I do this correctly, I'll put 1 out here, 1, 2, 3, 4. That should be good enough in that direction. And then the scale on the y-axis is going to have to be completely different. I'm going to have to count by like tens, I think. So like 10, 20, 30, 40, 50, 60, 70, and so on. And then going down in the other direction, 10, 20, 30, and so on. I think that's going to be all I need. So what I do know is that at the left endpoint, over here at -1, because this is going to be a graph from -1 to 4. At -1, I'm pretty sure that the graph starts right about there, and that is going to be the point -1, 37. That's a 7, believe it or not. Okay, then the graph comes down, goes through the origin, back up to a point right about there, which I'm going to leave blank for a second. Going to come down, do something like this, go up to here. And then let's see, where else does this thing go? So I think someplace down here, this is going to be some x value, which I'm going to leave blank, -27. Something like this. And then it's going to go back up. I don't remember exactly what the x-intercept is there. And then I don't actually remember what the highest value is over here. It stops someplace over there, and I don't remember what that is. But I'm pretty sure that it's lower than the 37 on the left. So I'll just put a dot. I'll just put a dot there somewhere. I don't remember exactly what it is. You could obviously plug in 4 to your function there and figure out what that actual value is. Pretty sure it's lower than 37. So again, all I want you to do is kind of locate the absolute max, the absolute min, and then we want to find the local max and local min values, if there are any, because there don't have to be. You can have absolutes, but you don't have to have locals. Okay, so the absolute maximum, that should be the easy one. I've given that to you. It's the highest possible value on the graph. It is 37. Remember, it's the y value. The absolute minimum, I have also given that one to you. That's another easy one. That's -27 at whatever x value that is that occurs. It's the locals where you're going to have to do some work. Now, if you're unfamiliar with how to do this in your calculator, you can go to your second trace and it should be an option to do a maximum and minimum. What you have to do is you have to kind of pick that open interval that you think surrounds the x values. Well, the first one being at 0 makes it easy. You can pick some value to the left of 0, some value to the right of 0, and then let it tell you what it is. It's pretty obvious on this one that you have a local minimum right there, and it happens to go through the origin, so we know that 0 is one of them. It also looks like I also have a local minimum here, which we already know is -27. It's the maximum one that we don't have, and I did fortunately find this earlier. So the maximum right there, again, you would have to plug that in your calculator for now because I didn't give you a way to do it otherwise, occurs at whatever x value that is. I don't actually know that, but the highest value, the y value there, is 5. And again, you would go to second trace in your calculator and kind of surround that value right there, and it would tell you that the y value is 5. All right, so that's going to be enough for this particular video. We'll come back and do a second video and finish it off.